So let us start with the next thing, that is order of reaction. So it has been already discussed in earlier videos also, or those who have attended the live lectures, those will be aware. Many a times I talked about the order of reaction. So if you consider a reaction, it might be just a repetition also. So if you consider such reaction like this, then the rate of the reaction is equal to K, that is the rate constant, concentration of A to the power X and concentration of B to the power Y. So what is this rate of the reaction? That is X plus Y. This is the overall order of the reaction. So if you add these two things, that will be the overall order of the reaction, isn't it? So in this way, you can determine the order of the reaction, overall order of the reaction. So for this purpose, you need to know the rate law. So this rate law has to be known, then only it is possible for you to decide the order of the reaction. Unless and until. So now, as I already told that this X and Y may be equal to a or small b, or it might not be equal. So this X may be equal to a, or this Y may be equal to b, which are the stoichiometric coefficient. So it has been already discussed uh, in the earlier videos and in earlier live lectures also. So for example, if you had such type of equation in front of you, for example, H2O2, it gives twice H2O. Now you need to have here the balance equation. Remember, the equation should be balanced to determine the order of the reaction. Now this is experimentally determined rate law. Now in earlier videos, I explained how to determine the rate law also. With example, if the data is given, you will be able to determine the rate law also, isn't it? So now this is equal to, rate is equal to K into concentration of H2O2, as there is only one reactant on the left hand side. So the looking at this, you can easily say that this is the first order reaction. This is first order reaction. Okay, because you know the rate law, means while deciding the order of the reaction, you need to know the rate equation or rate law. Then only it is possible for you to determine the order of the reaction. Now here, this is the one example where you can easily determine the order. If you have such equation in front of you, H2 plus I2 gaseous, and it is giving twice HI hydrogen iodide gaseous reaction. If the rate law is given like this, rate R is equal to K into concentration of H2 and concentration of I2. Where by looking at this rate law, you can easily say that this X equals to 1 and Y equal to 1. As there is nothing is written, means it is raised to 1, isn't it? So when X equal to 1 and Y equal to 1, so when you add this X plus Y, it is equal to 2. So this reaction is a second order reaction. Okay, so you need to know, I repeat, you need to know the rate law, then only it is possible for you whether the reaction is first order or a second order. Now the next thing, here it is an example where the reaction is first order. This is an example where the reaction is second order. Now this order can be integer or it can be fraction also. Now if you have the third example like this, third one, CH3CHO aldehyde, it is giving CH4 methane plus carbon monoxide decomposition reaction here. So the rate it is given by K into CH3CHO raised to 3 by 2. So this is the known experimentally determined quantity. Means from the data, when you carry out the reaction and you will get this equation from the experimental values, as I explained earlier in the earlier videos. So if you get this equation, so this 3 by 2 How it will come? By knowing the experimental data, means by carrying out the reaction, means this is acetaldehyde getting decomposed into methane and carbon monoxide. So you can stop the reaction at any instant, and you can find out the formation, or how many moles of this methane and carbon monoxide is formed, and how does it affect the rate of the reaction. So these things can be done either by titrimetric, or different methods are there where you can be able to find the concentrations of the product which are formed, and the concentration, what is the change in the concentration of the reactant. Okay, so by doing some exercise on this, you will get this equation. Now here, the order of the reaction, by looking at this, order of the reaction will be equal to 3 by 2, isn't it? Means unless and until you are not aware about the rate law, it is not possible for you to find the order of the reaction. Now the fourth example I can quote, the order of the reaction, it can be 0 also. Okay, so in this equation, if you have this equation in front of you, NO2 reacting with carbon monoxide to with this NO plus CO2. So in this particular reaction, the rate law or rate is given as K into concentration of NO2 raised to 2. Okay. Now it means that the order of the reaction, I'll write here, order of reaction with respect to, I'll write in short, with respect to NO2, it is 2. With respect to NO2, it is 2, and with CO, here there is no mention of carbon monoxide. This carbon monoxide, it is not mentioned in this rate law. So it means that with respect to CO, it is 0. Or it means that the order of the reaction, it is independent of concentration of carbon monoxide. It means that. Okay. Means here the order of the reaction for this above equation is, or for the above reaction is 2. Order for this, here it is 2 here, because this x equals to 2 here, isn't it? So this is an example where the order can be fraction. Here the reaction, uh, here where the order of the reaction, it can be 0 also, means with respect to CO it is 0, and with respect to NO2 it is 2. Okay, so this is the way you will be able to decide the order of the reaction. Now the next concept will proceed for the molecularity of the reaction. Molecularity. Now for determining the order of the reaction, you just remember, you just have to add the values of x and y, which is raised to the power of the concentration of the reactants. That is enough for you. So molecularity of the reaction or elementary reaction, as I already discussed, or it has been already discussed, that elementary reactions are the single step reactions. So molecularity of elementary reaction, suppose like this. Here, if you have this equation or this reaction, ozone molecule getting converted into oxygen plus nascent oxygen it is forming, or the C2H5 I, that is ethyl iodide, getting converted into C2H4, that is alkene, plus HI. Okay. Now, these are the single step reaction. These are called as the elementary reactions. Elementary reactions are those which occurs in a single step. There are no intermediate products here. So the molecularity of the elementary reaction, it is the number of reacting molecules taking part in it. Means just molecularity, it is nothing but the number of reactant taking part, in very simple way. Number of reactant molecules which are involved, that is called as the molecularity, isn't it? Now in case of this, if you take this example like this, NO2 here, it is getting converted into twice NO plus O2, and the rate is found to be K to concentration of NO2 raised to 2. Now looking at this, you can easily say that this is second order reaction, isn't it? Looking at the rate law, this is second order reaction. And it is a, what will be the molecularity for this particular reaction? You can say that the order of the reaction is 2, and since there are 2 moles of this NO2, so the molecularity of this reaction is also 2. So you can say that here this reaction is a bimolecular reaction, isn't it? Now for this particular equation, C2H5I, C2H4 plus HI. Now for this reaction, I'll write here, rate is equal to K into concentration of C2H5I. Okay. Now you can easily say that this is first order reaction because value of X, it is 1 here, this is raised to 1. So this is first order reaction. But in this case, it is unimolecular also. There is only one molecule involved. So this is first order unimolecular reaction, isn't it? So in these above two examples, you can say that this is second order reaction and it is bimolecular, means the order of the reaction is also 2 and the molecularity of the reaction is also 2. In this case also the order of the reaction is 1 and the molecularity is also 1. But it is not so every time. Order and the molecularity of the reaction may be same or it may not be same. Okay, so this is decided by the rate determining step, that is RDS. Now what is this RDS? Rate determining step means the slow step if the reaction is a complex reaction. So this rate determining step, it will occur in a complex reaction. Complex reaction is that which occurs in multiple steps. So out of these multiple steps, if you suppose that the one of the step is a slower one, so the rate of that slow reaction or the slow step is the rate determining step. So the step in which the reaction is occurring very slow, that step will decide the rate of the reaction. Okay. So for example, if you have this equation again, NO2Cl getting converted into twice NO2 plus Cl2. Okay. Now this reaction, it occurs in 2 steps. So now we have come across the complex reaction. Up till now we were discussing about the elementary reaction. Now NO2Cl, here it is the K1, that is the rate constant, getting converted into NO2 plus Cl. Now second step for this particular reaction, this NO2Cl, since there are 2 moles of this NO2Cl, now this Cl gas here, again it is getting converted into NO2 plus Cl2. Okay. Now out of this one, this step is a slower one. This one. This is a slower reaction and you are getting here NO2 plus Cl2. Now this you can see here Cl is formed in this step and Cl is formed in this step, which further combine together to get the desired product, that is NO2 plus Cl2. So before reaching to this NO2 plus Cl2, especially this Cl2, it has come across 2 different steps. This is one and this is the second one. And after they combine together, you are getting the product here. Now, you can say here the net reaction for this, you can write here twice NO2Cl gaseous reaction getting converted into twice NO2 plus Cl2. Okay. Now, rate law for this is found to be rate equals to K into NO2Cl. Okay. Now looking at this rate law, you can easily say that this is first order reaction. Now, in the above reaction, what is happening? This Cl is formed in the first step and which is getting consumed in the second step. So it has been getting consumed in the second step, and such species is nothing but we call as the reaction intermediate. Now the concentration of this intermediate which is formed here, it does not appear in the rate law. You cannot see here the concentration of this in chlorine, which is Cl, which is a single atom I had shown here. It is not appearing in this rate law. So in this way, here, though this is a complex reaction, it is occurring in two steps, but the order of the reaction, it is the first order. Okay. Now, in your textbook, it is given that the difference between the order and the molecularity. Now, I won't be going into the much detail, which is a very simple thing to know. That is, order is nothing but the experimentally determined quantity. It can be determined experimentally. So order is nothing but experimentally determined. As I already discussed, x plus y, experimentally you can determine the order. And this molecularity is the theoretical one. With just looking at the reaction, you can be able to know the molecularity. So this is the theoretical one. So the order and the molecularity may be same or it might not be same also. Now this order is nothing but the sum of the power of the concentration of the reactant, like this, isn't it? This way. So addition of these two is the order of the reaction. Now it is the number of molecularity, it is the number of reactant molecules taking part in the reaction. Number of reactant molecules taking part in elementary reaction, taking part in elementary reaction. Okay, so this is about the elementary reaction. And the third point, it may be integer order, it may be fraction, as I explained earlier in the earlier examples, or it may be zero also. But this order of the reaction, it is always an integer. This very simple thing, that is that you can differentiate between the order and the molecularity of the reaction. Now, if we proceed further for the next one, that is the integrated rate law for the first order reaction. Now, up till now, we have discussed rate constant, rate law, order of the reaction, and the molecularity of the reaction. What is complex reaction, what is elementary reaction, and so on. Now, we came across the next concept, that is of the integrated rate law. Integrated rate law. If you have not understood either of the points, you can go to my earlier videos, which are already posted on the uploaded on the YouTube channel. So you can have the doubts clear for the first order reaction in solution. In solution. Now, up till now, if you have observed, we have been discussing about the gaseous reaction. Now we came across the reactions in which the solution is involved. Now, if you have this elementary reaction like this, A is getting converted into product. So rate for this can be written as minus sign indicates the consumption of the concentration of A equals to, that will be K into concentration of A. So what is this this A? This is the concentration of reactant at time t. At time t, that is nothing but the instantaneous rate of the reaction. Okay, so it has been already discussed in earlier videos also. So now if you rearrange this equation here, you can write like this, equals to minus K into dt. What did I do? I just rearrange this equation, this upper one. Okay, now you have got this equation which I label at equation number 1. Now this, suppose this concentration of A at 0 time This is the initial concentration of reactant A. Initial concentration of reactant A at time t equal to 0, means at 0 time or at the initial time. And suppose concentration of A to the base T, that is the concentration of reactant A at time t equal to T, or at time T you can say, or you can write at time T. It is one and the same thing. Okay. Now concentration of A can have two values. That is the initial concentration denoted by this thing at t equal to 0, and concentration of A at time you can write this way, isn't it? At t equal to T, means that is at that particular time. Now, since we are saying that it is an integrated rate law, now you can write further. I'll add one slide here. So for this one, you can write. So we need to integrate this equation. Okay. Now I'll write this equation again. This is very simple. You will understand this easily. So this is the equation number 1. Okay. Now we have these conditions as I already explained. Now integrate this between the limits, concentration of A at 0 time and concentration of A at T time. So you can write this way, this equation equals to minus K at 0 to T time, and on integrating, what you will get? On integration, you will get this thing. I hope you know this, it's much mathematics. Ln concentration of A to the concentration of T equals to minus K into T 0 to T. Now substitution of limits, it gives substitution of limits, you will get here like this. You just have to minus the things. Ln A0 equals to minus K into T. This is just a mathematical one. Or the same thing you can write concentration of A at time T divided by concentration of A at 0 time equals to minus KT. Isn't it? So now this will be your equation number 2. Now further you can write for this. I'll try to accommodate on the same slide for your understanding. Or you can write K equals to, in terms of K, 1 by T ln concentration of A at 0 time divided by concentration of A at T time. Now converting this ln to log to the base 10, that is a natural log, we can write K equals to 2.303 T divided by T log to the base 10 concentration of A at 0 time divided by concentration of A at T time. Okay, now you can number this as equation number 3. Now this further, this equation can be used to solve the numericals based on this. Remember. Now ln concentration of A divided by at T time divided by A0 equals to minus KT. So now we have these two equations. This one, equation number 3. So this is just the conversion of ln to the log to the base 10. Okay. Now by taking the antilog to the of the both sides, if you take the antilog to the both sides, you can write here concentration of A. When you take the antilog, you can write E raised to minus KT, or the same thing you can write concentration of A, just rearranging the equation, nothing else. 0 E into minus KT. So now this is your equation number 4. Okay. Now this same thing you can write in terms of the concentrations also. K equals to 2.303. Just concentrate on equation number 3. 2.303 log to the base 10 a divided by a minus x. So this equation and this equation number 3, it is one and the same thing, a upon a minus x. What is this a? If you take a is the initial concentration at time t, and suppose x moles of this is consumed or getting converted into product. So whatever is the left, that is a minus x, means that is the concentration of that decreases or reacts during time t, and the concentration of that a which is remain here unreacted at time t, that would be a minus x. So what is this a minus x? That is the remaining amount of the initial concentration which we have taken a. Okay. So this, of course, when you talk the concentration term, it should be always in terms of moles per dm cube. So this is the another equation which can be used to solve the problems based on this. This equation number 3 and this equation also. Means A is always considered as an initial one and this is the remaining one. Okay. So now this is your equation number 4 and this, if you number this as equation number 5. So 3, 4, 5, either of these equation can be used to solve the numericals based on this. So this is nothing but we call it as this equation is the integrated rate law. Means we have been discussing a lot about this instantaneous rate of reaction. Means whatever is the rate of reaction at that moment, that is very important when you study the rate of the reaction or overall rate of the reaction. And whatever is the amount is remain, that is also very important thing for you. So for this purpose, this equation, we are just integrated, means we are just combine the things together, integration. I hope you understand what is integration in mathematics. So this is the way this equation number 3 and this equation number 5, these two equations are very much of importance to solve the numericals based on this. Okay, so this is about the integrated rate law. Now, in the next lecture, we'll talk about the, we'll talk